Thank you. Whew. Hi, everyone. Today I'm going to talk about ReVault and how you can get compromised by your secure system on chip. One sec, laser pointer activated. So hi, I am Philippe Laulheret. I'm a senior Vault researcher at Cisco Talos. I focus on Windows and embedded systems. And basically, if you're not familiar with what we do, Talos is the threat intelligence branch of Cisco. And my team, we look for vulnerability in third-party software. When we find stuff, we report them to the vendors, they fix it, and then we can talk about it publicly and hopefully create detection rules or similar. So what can you expect from this presentation? It is a roughly 40-45 minute talk where I'm going to go over some of the vulnerabilities we've reported to Dell and Broadcom earlier this year, and which leads to full compromise of something called Control Vault. So here you can see a Dell laptop, and over here, you can see, over here you have a fingerprint reader, here an NFC card reader, and on the side you have a smart card reader. And all of those devices are actually connected onto that thing called Control Vault. If you open the device manager, you will see this Control Vault device, which is kind of mysterious looking. And if you open your laptop and remove the battery, you can find the actual Control Vault device here, and it connects to the motherboard over there, and all the other peripherals are connected to it. The smart card reader, NFC, and so on. So at this point, you should be Control Vault, what is that, right? So to give you a brief summary, you can find it in actually 100 models of Dell laptops. So mostly the business one, so the Latitude and Precisions, and also the new one, the Dell Pro. It's a mix of software, firmware, and hardware. So you have host APIs on Windows or Linux, and then you have a firmware running on that little board here, and specifically on that chip, which is a Broadcom BCM58202. And on the chip, it's an ARM chip, and it runs a real-time operating system. Technically, it's meant to be a secure storage of secrets, or at least it used to be, not so much anymore. And the flash share is encrypted. And it's also called the Unified Secure Hub, because, as I said, you can connect a different peripheral onto it. Technically, it's Control Vault 3. There's actually 3 Plus for the Dell Pro. And before that, you had Control Vault 1 and 2. Control Vault 1 was 2010, 2 I don't remember, and Control Vault 3 was 2019, I think. And so roughly back the envelope, it's tens of millions of devices have Control Vault 3 or 3 Plus. And both are vulnerable to what I'm talking about today. Or at least until you get fixed. I mean, until you install the patch. And there is no documentation, so we got to do some research. So first step, we can Google stuff. And one of the interesting findings is this link here, which is actually just the Linux host API. So if you have a Linux machine, you can install that. But what is interesting about it is it comes with a shared object, like an SO file, which was compiled with debug symbols. So if you import that in IDA, Ghidra, or similar, you will have a lot of information, including a lot of data structures, enum, error codes, and so on. And those values are used in both the host side, but also on the firmware side, which becomes extremely useful to understand how the firmware works. And that one was kind of fun. It's a certification for the cryptography module on the system on chip. Doesn't give much information at all. Gives some ideas of how it's meant to be used, but it's really light. But it also provides some acronym definitions. For instance, here you have something called SBI, which stands for Secure Boot Image, and it's an extension of the boot ROM on the chip. That will become useful later. So now you could be why did I want to target that? Beyond the fact that tens of millions of devices could have that. Well, the beginning of that project was much more humble. I was looking at stuff running on my machine, and I spotted that where, if you notice it, there is ASLR that's missing. So ASLR stands for Address Space Layout Randomization. And so I was looking for things that didn't implement that because in this day and age, everything should. So if it doesn't, it's not the great sign. And fun fact, it's running as a system. So I was ooh, that looks spicy. And the same, the DLL loaded by that thing doesn't have ASLR either. So I got really excited, and I was let's hack the planet, guys. And so, but calm your enthusiasm. And first, let's dig deeper. look at the files that come with Control Vault, and there's like so many of them. You have driver for the USB stack, the fingerprint reader, the smart card reader, the NFC card. You have a lot of Windows services, including stuff that are like not even used, so that was kind of curious. And there's like a firmware folder, and inside there's like a bunch of files, including this famous like SBI image. And that's nice, it's in clear text, so like you can open that in IDA and start reversing if you want. And then you have that thing called Citadel, which is actually the application firmware, and that one unfortunately is encrypted. So that kind of like, back the, oh, we want to find what's hidden inside, because that's the main thing we're talking with, on your machine. So that's going to be like our next step, like soon. But before we go too far, like, just to give an overview of the system architecture. So here you have the Control Vault device that talk over USB with the host, and on the host you have like a USB driver, like kernel side, and then you have like APIs that are fed into different services and user and drivers and so on. And on the other side, you have like the actual hardware, like like your smart card reader, your fingerprint reader, which are all talking with the USH board, like the Control Vault board, over various like buses. And inside, as I said, you have the SBI, that's certain application firmware, and before that you have a boot ROM that check the SBI. So if you want to talk with your Control Vault board, like in your laptop, the way it works is that first, the driver, like the USB driver, is going to create a device, and user land can open that device and send a device IO control to it. And eventually, the driver will send USB packets to the firmware. But that's kind of really tedious to do manually, so it turns out that Broadcom made like a userland API that is not for you to use, but for them. And that implements a lot of high-level functions, so something called like CV open, CV close, create objects, get objects, etc. And like CV stands for Control Vault, right? And most of those functions require like to first call CV open to get a handle and start the session and so on. On the firmware side, you have a function called CV manager, which basically receives the CV commands and then dispatch it to the appropriate function. And all of that is really interesting target. I think there is like 150 CV commands, so there's like a lot to look at. But we can do like baby steps, and with this, I don't know, 20 lines of Python, hopefully you guys can see. But basically, you just open the DLL, the user and DLL, and you tell Python what type of parameters that function expects, and you can find that from, for instance, the symbols in the shared object on Linux, if you want. That's the same stuff. And in that case, for instance, the CV get USH version, which is a function to return the version string of your device. And so if you run that in Python, boom, you get like the version string of your device, which is really fun because it's like 20 lines of Python, and now you can actually communicate with this mysterious device inside your laptop, which I think is really cool. Okay, now that we know how to talk with the board, like what can we do, what can we mess with? So same diagram as before, but this time we can focus on like attack surface. So I think 4 main interesting points. So first is this whole like firmware side, obviously. Like you have the SBI and the application firmware, have like a USB stack, run some CV commands, and have also a way to interact with like Windows services. That's a lot, a lot can go wrong there. So definitely something we want to look at. Then the whole firmware itself supposedly implements something called secure boot, which basically is meant to prevent you from modifying the code running on the firmware. But we should double check, do they do it right? So how does the firmware update mechanism work, and how the signature check works? Because if we can modify the firmware, that's not great. Then on the Windows side, there's like a lot of interesting stuff as well. Maybe we can mess with the driver, maybe we can mess with the services that run a system, and don't have ASLR, all spicy targets. And the last one that actually I did not look at because there was a lot of scope increase is that side. I think it would be really interesting to consider, like, if you have a malicious fingerprint reader, for instance, could it compromise the firmware, the SBI and the application firmware here? Or alternatively, could a malicious firmware mess with the fingerprint reader? So yeah, all of those are really good questions, but trying to look for them would increase the scope of that work by 10x, so didn't do it. But if someone wants to pick up the work, that's an interesting opportunity. Just to double down on the secure boot aspect, this is kind of a schematic version of it. So the boot ROM will verify the SBI, and the SBI loads something called the secure code description that contains some key material, and with that, it's able to start the application firmware. And from like a firmware update perspective, all of this area can be modified. So we want to check how secure that is. So just to get an idea. Now we want to mess with stuff. So what is going to stop us from messing with it? On the Windows side, as I said, like the Broadcom services don't have ASLR, but they have DEP, which is like data execution prevention. So basically, you cannot just put a payload on the stack and jump into it. You have to do a little more effort. And there's like something else called like stack cookies, which are meant to prevent easy exploitation of Stack Overflow. And in that case, some functions have a stack cookie and some don't. So that kind of depends. I'm not sure why, questionable compiler flags probably. And the control vault firmware, it has a really cool feature called like encrypted execution in place. So the firmware is encrypted on the flash, and it will be executed like that, which is really cool, I think. And then, there is like secure boot I was talking about. But then there is no ASLR, so we know like the address of the code in memory. There is no stack cookie, so if we can get a Stack Overflow, it's game over. I think there is DEP, so we cannot jump on the stack. I think it seems like the board seems to crash, so probably not, but I'm honestly not entirely sure. But there are read-write execute regions like mapped in memory that I found that like through reversing. So basically, if you can put your payload in one of those regions and just jump into it, like it's game over and you get a full compromise of the board. So let's see if we can get there. So remember, the problem we had was that the main application was encrypted, but the boot image that starts it is not. So we're going to hope that the SBI knows how to decrypt the main firmware. And for that, we're going to look for firmware decryption routines. And the best is to start like looking for strings. And we find all of those mention of decryption failure, which, not good for the firmware, but for us, it's a bit of a success because it's actually pointing us to how the firmware is being decrypted. So in practice, it takes like 3 steps to do a firmware update. And that's like done from the host. And you find that by reversing like the various binaries and whatnot. So first step, it's going to call upgrade start. And the host is going to send the encrypted header of the firmware. And the firmware itself is going to decrypt that. And if there is no key material like in memory, it's going to default to like hard-coded defaults, which is nice because we don't have any key material at this point. So we're going to hope the defaults work. And then what it does is generate a new key material to store the new firmware like encrypted on the flash. So it's a curious like setup, but that's the way it is. Then it calls like upgrade update, and it's going to like send a bunch like the remaining of the firmware by chunks, and those get decrypted. There's like a rolling hash to make sure that the signature of the whole thing is good. And it has like this weird IV computation for the cryptography, and I'm going to show that in the next slide. And finally, when it's done, it calls upgrade complete, verify the signature of the firmware, sorry. And then if it's good, commit that to the flash, and it's done. In practice, that looks like that. Upgrade start. You can see here it's loading the default key and default IV in that structure here. And then it's being passed to the decrypt function. If we look into the decrypt function, it's really just a wrapper around the crypto module of the chip. So we don't really know which kind of algorithm it is, but we have some idea from the certification we've seen like previously. And really the trick is we can just try all of the potential algorithm until we find the one that works. And it turns out that's ASCBC, and it's indeed using the default key and IV. And there's like many SBI like in the firmware, so like one of them they have a different key material, but the other ones are good. And when we decrypt that, it looks like that. And we see that there is like a lot of 0 bytes. It's not random data, so we know we decrypted the thing successfully. And there's like some fields, some values, and just be careful because the endianness can swap depending on the way the firmware is used, so that can lead to trouble. And we'll see that in a minute. And then, so that was decrypting the header of the firmware, and then it's the main loop that decrypts the rest. And as I said here, it's like using the same stuff, but it's instead of using the default IV, it's computing one based on the address of the blob of data you're trying to decrypt. And that's the function that does the magic. So in practice, like if you want to re-implement the algorithm yourself, you just copy-paste that into Visual Studio or Python, and you run it. Doesn't really matter like the math. But yeah, so you plop the numbers and it works. And so you run that for a while, you decrypt the firmware, and eventually you have a decrypted application firmware. And that's nice because now we can start looking for actual vulnerabilities. It's time to hack the planet. So as I mentioned, when we talk with the firmware, you have like the CV commands, and to start one, you want to call CV open. And CV open create a session, and on the firmware side, that looks like that. First, you allocate memory. Then it writes a session tag, so the letter SESS. And then it's pretty much it. The pointer to that object gets passed as a handle back to the host, and that's it. Which I think is quite curious because it's immediately like leaking like heap address back to the host. And it's not necessarily a vulnerability in itself, but it's still like quite a questionable design decision. But yeah, so now we open stuff, so we're like well educated, so we also close them. So CV close, what it does, take the pointer to the session and validate the session. And to validate the session, it makes sure that the address is in the proper range, it's like within the heap. Verify that the session tag is actually present, make sure that you have like the SESS letters, and that's pretty much it. And then, erase the tag and free the memory. But now, like if you guys like to play CTF, maybe your like spidey sense are tinkling, because really like the only check is the right range of memory and like 4 bytes of data. So you're like, maybe you can create like an arbitrary free, like if you could place a fake session object, on the heap, you could probably free it, like the checks are quite brittle. But can we do that? Well, yes. We have a function called CVCreateObject that lets you put some data on the heap. So you can create an object that will start with SESS, and it would look a lot like a valid session. But there's like a few gotcha here. One is there's like a bunch of metadata in that object that we don't control, and also the handle we get for that object is not like the address of the object like it was for the session, but instead it's just some random number. So we don't know on the heap where is our object. But that's not too much of an issue because what we can do is like we can look for it. And I picked like some other function, in that case CVGetRandom, which is meant to return random data from the crypto module, which I think is pretty cool, but irrelevant here. And what it does is take a session, and depending if the session is valid or not, we'll return a different error code. And so what we can do is just like try all the potential values that would be like the address of the object we've just created and see if it is being recognized as a valid session. And with that, we have like a session oracle that doesn't have any kind of like side effects. So that's nice because with that we can locate our object. So just to summarize a little, with createObject, we can place data on the heap. I didn't show this function, but getObject and setObjects, lets you like retrieve or set data of those objects. GetRandom can be used to locate, a session-looking object, and CVClose can be used to free like an object that looks like a session. So with all of that together, we do have an arbitrary free in the CV heap. So now is it like heap exploitation time? That's me when I have to do that because I don't like those kind of CTF problems. So I was like, you know what? Let's find more bugs. Maybe we can put a pin on that one and find better ways to exploit that. So I kept looking at stuff, and I found like this function called secureBioIdentify. It doesn't have a CV in the name, but it's also a CV function. Takes an object handle, and what it does, retrieve the properties of that object, and then memcopy into this data2 field here, like one of those property value, and data2 is some like stack variable. So here I was, like rubbing my hands. I was like, ooh, do we have like, a Stack Overflow with that object value? So not so quick, because for that we need to be able to put control that object value and have it way too big. In practice, you cannot do that during object creation, but that's not a problem because we have a heap corruption primitive, and so we can tamper with the heap and forge or modify the metadata of a CV object to make it look like the field is way bigger than intended. And to give an idea of what it looks like in practice, so that would be like an object that's been allocated with the SESS tag that we put there. And purple would be what we can modify, and blue would be stuff we cannot modify because it's metadata of the object. But what we can do is relocate it, free it using our CV clause function. And now we basically poked a hole inside our object, and we can allocate a new object that's going to be smaller. And because the way the heap is implemented is going to be placed inside the hole we just poked. And what's interesting is, here we have the purple side overlaps with the blue side. So we can modify the data of the big object, and it's actually going to modify the metadata of the smaller object that we have overlapped. And with that, we can put malicious data into there. And then we can feed the smaller objects into secure bioidentify and trigger the Stack Overflow. So just TLDR for the exploitation. As I said, there is no ASLR, so we can just do some really simple web chains. I just wrote some IDA Python script to locate gadgets that would be useful for that. And then we can use the ROP to memcopy any payload into the read-write-execute region we found through reversing. And then we just hope we don't overwrite something important, and we can just jump into it. And we check, and if it works, yes, we can actually execute code. So that's nice. Now we have code execution on the firmware. But what do we want to do? So there's a few ideas I had. The first one was we can actually return any arbitrary data to userland. So the idea for that would be to run the exploit and then write data inside the large object we've created and use the CV get object function to retrieve the output of our exploit back to the host and leak useful information. For instance, we can dump the RAM, we can dump the boot ROM, which happen to be mapped in memory. But there is another one that's really cool. It's called the SOTP read key, which is used. You're not supposed to be able to call that one, but we have code execution, so we can. And it basically retrieves key material that is stored in the fuse of the chip. And obviously, we don't know quite yet what the keys are, but we kind of want that because it sounds cool, So that's one angle. The other angle could be patching the function pointers in memory. So vtables or just straight out function pointers. And this way we could hook the execution of certain parts of the firmware and execute custom payloads. So the idea being baby steps towards firmware modification. That works, but I'm not going to talk about that because we'll have a better way to do that stuff in 10 minutes. So first demo, I'm going to showcase how we can dump the keys of the device I had. So in practice, first step is to locate existing session because the computer was in use. Then we create our own fake session, we free it. After that, we exploit the secure bioidentify to call SOTP read key. We do that twice. And we leaked two device keys, like an HMAC key and an AES key. And those are not blurred because that's my machine and not, it's only works for my machine. So it's okay. Now you'll be okay, keys? What kind of keys? What are those keys? What's going on here? So TLDR for that. There's roughly 7 fused key in the chip, in the firmware. 2 are used for AES and HMAC to encrypt and authenticate, I guess, the flash, the secure storage on the flash, and also that stuff I mentioned before called the secure code descriptor. And the secure code descriptor also contains key material, and in particular as an ERISA key that's used during firmware verification, firmware update to verify the signature of the firmware that's been updated, and the AES and HMAC keys that are used for the execution in place, because as I said, the whole chip is encrypted. And then we have hard-coded default keys, and those are actually being used when the SCD is invalid. And the question is how does that happen? How do you break your SCD? It's something important. Well, it turns out there is a file, in the firmware folder I was mentioning called clearscd.bin, And I don't know if you guys can see, but it's just like 0, 1 to F a bunch of time. And it's actually used legitimately by the firmware update mechanism. During the update, the host is going to flash that over like the normal SCD using a function called cv-flash-update. And then reboot, and when you reboot, the SBI is going to try to load that SCD and gets extremely confused because that's not a valid SCD and it's just junk. And then it stops there and waits for an actual like firmware update, which I think is pretty bonker from like a design perspective. Like, why would you do it that way? I don't know. But what is spicy here is that we actually have an arbitrary flash write, from the host, and that's a feature. That's not even a bug. That being said, in theory, the whole flash is encrypted, so being able to write stuff that's going to decrypt as junk is not extremely useful, but we just leak the keys for flash, so now we can actually write interesting stuff in the flash. Which begs the question, how secure is the boot process, now that we can mess with, do stuff. So we can revisit the diagram I had before, and there's like little more details. So the way it works during secure boot, the boot ROM is going to verify the secure boot image, and the secure boot image is going to get the fuse key and use that to decrypt the secure code descriptor, which contains those key material, which is going to be used to populate the encrypted execution in place like engine. And then we start the application firmware. And here what's spicy is that there is no signature check of the application at boot. That part is never like verified. The security of that thing depends only on the security of the OTP keys and the secure code description. So, maybe you guys see where I'm going with that. It would be really fun to be able to do some firmware modification. And in theory, like what we can do, we can dump the device keys, just showed you how. We can retrieve the secure code descriptor content and decrypt that. And then that's the part that gets a little tricky, we could, in theory, forge, blobs of data with the proper encryption and HMAC, and then reflash that. But there is a risk. Is like if you try to reflash, the code that's being executed, at the same time, it's like you're going to brick your device. It's not a good idea. But another angle, which actually is more easier, we can forge a new secure code descriptor, but replace the RSA key that was used for firmware verification with our own key, and we have the private key of that one. And then we can forge a firmware update that will verify successfully with our forged key, That will only work for our device, but that's what we want. So, did it work? No. I bricked the device because, and you can see here, I'm trying to restore it. And it didn't work just because I flashed the wrong STD, the byte orders were reversed. And that was it. But that was, I thought about it, I was like, I don't want to brick my laptop. So I made a copy of the flash, and here I can be seen reflashing it to fix it. So I put back everything together, it works again. And I reflashed the SCD, but this time with the proper Indianness, and it works this time. So we can see maybe here it says control pwned. So that's when the device talks to the USB bus to my host, it says, oh, I'm pwned now. So the application firmware was modified. It will persist even if you reinstall Windows, because that's nothing to do with Windows. It's the firmware has been modified. And so here you have a potential permanent implant in the system, which is pretty cool. And so yeah, as said, the device was called the Unified Secure Hub. But how is it secure now that we can actually modify the code that runs on it? So it turns out there is a function called CV fingerprint identify, which is used when you want to log in onto your laptop using your fingerprint. It's like talking with Windows Hello. But the matching of the fingerprint is done, on the firmware. So because we can change the firmware, what would happen if you could make it say yes all the time? It's like, oh, do you recognize the finger? Yes, it's me, yeah. So in practice, that's what it looks like. I flashed on this laptop a custom firmware, on the control vault device, that will accept any finger that's being presented on the fingerprint reader as valid. And in that case, I have a little plastic finger, and I taped some green onion onto it. And when I touch it, it unlocked the laptop. So that's pretty cool. And so here we see that we can bypass fingerprint login through that mean. That's nice, but we want to mess with Windows too. That was the initial goal. So what we can do? Before I go too far in that, I need to give some details about how data is being passed from the host to the firmware and vice versa. So when you send a CV command, the host is going to prepare the arguments. And there is this tag length value type of thing where you specify how the data is going to be encapsulated and decapsulated. For instance, the first one here on that line is when the data is being decapsulated, it will just be copied into a raw buffer. And that one is actually, the third one actually says, instead of just copying to the buffer, it's going to split in two. One value is going to be the size of the buffer, and the rest will be the actual buffer. That's going to be important in a sec. And so what happened next is the host prepare, allocate the buffers, make the proper encapsulation types and whatnot, serialize everything, send the command to the firmware, and upon returns, the data is going to be deserialized, and the parameters are copied back to the user. So in practice, that looks like that. On the host, you have here the creation of the going to the firmware and going back from the firmware list of parameters. And you can see here they're using that len-vol pair, so that the type 3 or whatever. You call the function, in that case cv-get-random, and upon return, it's going to decapsulate the data and split it into the size and buffer as I discussed a second ago. But it turns out the firmware is being trusted too much, because if you look at firmware side, when it receives a cv-get-random command, it's going to redefine the encapsulation type and the size. And it turns out that the host actually trusts that new serialization. So if you have a malicious firmware that sends, the wrong type of data or too much data, it totally leads to overflows and type confusions. Practically, what it looks like, we can backdoor cv-get-random to make it so that it will be malicious in certain circumstances. So the way it looks like, as I said, you have the parameters are expected to be an integer for the size of the data that was generated and the buffer. But if we change the encapsulation type for the first type, the plen value is going to be considered as the buffer instead of being an integer on the stack, and that should lead to a stack overflow. And in practice, we don't want to break the whole system, so we're going to modify cv-get-random to only do that if you request a specific size, magic size of data, to basically signify, oh, I want the backdoored version instead of the normal one. And the result would be to treat plen as a buffer instead of the integer IDs, which will lead to a stack overflow. So in practice, that looks like that. So that video is a little crappy, but on the right side, I have made a toy binary that just call cv-get-random, and here's the function that does it. And the idea is, if you just call it without arguments, it's going to call the normal cv-get-random. And if you put a command line argument instead, it's going to use that magic backdoor value to trigger the bug we put in the firmware. And it's actually going to exploit Windows, and it's start a calc. So with that, we're able to compromise a legitimate, the Windows side of thing from a malicious firmware. But you can be like, well, that was a toy binary, that's not really important. That's true. But the goal was we wanted to exploit the system service. And so let's see if we can do that as well. But we need to find something that runs with a high privilege, use the control vault DLL, and doesn't have the stack cookie situation I was talking about. So some targets, the Broadcom services, some third-party application. I couldn't find any, unfortunately. They stopped making them, apparently. Or Windows Hello, that's being used to talk with the fingerprint reader. So I spent hours looking at all the functions, the CV commands, how they were implemented. I'm really sad because it takes a lot of effort. And eventually, I found Broadcom Storage Adapter DLL, which is used by Windows Hello as a kind of the glue code to talk with the fingerprint reader of our system. And so that's Broadcom wrote that thing. It's nothing. It's It's not a Windows Hello DLL, it's a Broadcom DLL that talks with Windows. Anyway, the function here takes a handle to an object, get the object, and copy basically fill the header of that object. And CV get object can be compromised the same way we compromise CV get random. And yeah, the object header here is on the stack, is actually like after the end of its own stack frame, and it's in its parent stack frame for some reason. But we can see here like the return address is here and there is no stack cookie in between. So if we can overflow our object header, we can overflow the return address and gain code execution. So in practice, how does that work? That whole stuff is used by the Windows biometrics service to implement like fingerprint handling. And it turns out that it exposes a IOCTL-like interface so that like any user can send commands to the fingerprint driver. And that's the call stack. So we can mess with that one, and create an overflow that will basically compromise the whole stack. Yeah, that's what I just said. And in practice, how it looks like. So in that situation, I flashed, that malicious firmware that backdoored the CV get object. And on the right side here, you're going to have the Windows biometrics service, that runs the system. And when the firmware has been uploaded, so I'm going to just call that IOCTL command with a magic, handle that triggered the backdoor, and that's meant to exploit the Windows biometrics service. So, and it's going to run some shell command that I put in there. So we call the backdoor, and we can see here it starts like netcat under SVC host, and we can connect to it to have like a nice remote shell. And we can see here that we're running as a system. So with that, we've shown that a malicious firmware can actually compromise a legitimate binary on Windows and gain system access. So that's what we've done so far. We got CAD execution on the application firmware. We modify permanently the firmware if we want. We can bypass Windows login screen, and we can get like system privileges. Is there anything else we can do? Yes, this is like a fun one. As I mentioned before, that board, so that's the one I got on eBay, connects to your motherboard with this little ribbon cable, and it's like an internal USB device. And I was like, well, would it be nice if you could, take your board and plug it on an external USB, so that you can mess with a board more easily. And in practice, that looked like that. All the wires. In theory, I was going to design a little PCB that make it nice, but I didn't have time, and so it's that mess. But basically, all those cables are like 5 volt, 3 volt, and the USB line. And so in practice, that board is connected over USB, and when I plug the USB, you can see that a new control volt device will show up like here. So now, like that laptop has 2 devices, and I disabled the one that's internal. And here I'm showing that we can actually interface with that external board, over USB. So that's cool, which means like here we've actually unlocked like a new physical attack angle. Someone could take your laptop, remove the battery, unplug the cable from your motherboard, plug it into this little contraption, and directly hack the board that's inside your laptop, from a separate machine, and have this kind of evil maid attack type of thing if you leave your laptop unattended. Pretty fun. So just to give a TLDR of the meaningful attack scenarios, there's 2 main ones. One would be a user has been compromised, clicked on the wrong link or something, and the threat actor could actually, modify the firmware of their device and basically maintain a foothold inside their machine that could persist even past, a Windows update, or a complete reinstall of the machine. So that's one angle. And then another angle is someone with physical access to your machine could, open the machine and mess with the board that way. And from there, bypass the fingerprint login or also compromise Windows. So the findings, we reported the stuff to Dell, earlier this year, and they released 2 advisories, one in June and one 3 days ago, or a week ago. All the reports are available on the Talos website. So if you want to read the technical details, you can. Bunch of CVEs, and a few more that didn't fit on the slide. And there's like 2 write-ups also on the Talos website, so if you want the technical details, you can read them there. So yeah, I think that's pretty much all I have. I think what's important to think about here is that firmware security is not necessarily like, the newest, the most glamorous topic, but I think it's incredible that we have those boards in our laptops. It's been there for like 10 plus years. Nobody has ever documented them. We don't know what they do. And they have like incredible like access and impact. So I think, from a security perspective, if you like reversing, maybe you should look into this kind of stuff to understand, what's in the machine. And if you're more on the defensive side or like customer side, maybe we should all ask, Dell and, other, well, I don't want to name them, but we should ask or provide like the device manufacturer to provide more transparency into like, what's in the system so that, we have a better understanding of the risks. So yeah, I think that's all I have. You can find me on Twitter or Blue Sky or wherever. And if you have questions, I think we have maybe 3-4 minutes. And otherwise, you can find me later. Thank you. Any questions? Cool. Well, I guess you guys can enjoy lunch. Thank you, guys.